In previous lectures, we studied divide and conquer algorithm design technique, and we studied 5 representative problems. First was defective chessboard problem, having 4 subproblems. Second was Karatsuba's integer multiplication algorithm, where we get 3 subproblems. Then we studied Strazen's matrix multiplication algorithm, where we derived 7 subproblems. Then Gaussian elimination with only 1 subproblem, and finally fast Fourier transform having 2 subproblems. So we know in divide and conquer we have basically 3 steps. First is divide. We divide the original problem into smaller subproblems. Second, we recursively solve the subproblems. And third, conquer. We combine the solution of smaller subproblems. And this recursion step, we do this until base case. Base case we cannot further subdivide and solve it trivially. So this is the idea behind divide and conquer. So today we'll study our first problem for which we designed greedy algorithm is the fractional knapsack problem. So for this problem we designed greedy algorithm. So greedy algorithm we'll see it differs from how it differs from divide and conquer. So first thing is we incrementally build the solution. Incrementally build the solution. So suppose we have to do some optimization, like find some minimum or maximum value. So how we build the solution? We incrementally build the solution. This is first characteristic of greedy algorithm. Second thing is locally optimum choice. Locally optimum choice leads to globally optimal solution. This is the second property. So at each step we make local choice, either maximum or minimum, and this is such that if we keep making the choice, ultimately we get globally optimum solution. This is called greedy choice property. It has a name, greedy choice property. So this is the most difficult part in designing greedy algorithm. We have to prove that our algorithm has greedy choice property. If we are unable to prove, then our algorithm will not work. So this is the only difficulty with greedy algorithm. Usually greedy algorithms are very simple because we are making locally optimum choice. Most difficult part is proving greedy choice property. And third characteristic is single subproblem. So this greedy choice property leads to a single subproblem. So a larger problem becomes a smaller problem, and even before solving the subproblem we know our partial solution. So we incrementally build the solution, and how we build, we make local choice, locally optimal choice, either maximum or minimum, and we keep on doing this, and this leads to globally optimal solution. We have only a single subproblem. So these are 3 properties of greedy algorithm. Now we'll define fractional knapsack problem, and then a very simple greedy algorithm, and then prove its optimality. We'll prove its greedy choice property. So the problem is called fractional knapsack problem. So fractional knapsack problem, we are given n items. So the input is in this format. Given n items, name the items I1 up to capital I1 up to In. These are n items. So each item has some weight and profit. So corresponding weights we have. Weights are denoted as W1 up to Wn. Each item has a weight and also a profit, which we denote by variable P. Profits are P1 up to Pn. So n items are given having some weight and some profit, and also a knapsack capacity capital W is given. Knapsack capacity capital W is given. So we have to fill the items in the knapsack, and it is such that it can hold items only of total weight maximum up to capital W, not more. So we have to fill the items in the knapsack, and one more thing is that we can take a fraction of an item. So this is the reason the problem is called fractional knapsack. Fractional means we are free to choose a fraction of any item. Fraction, for example, we can take half the item, so its weight will be half, profit will also be half. So the corresponding fraction of weight as well as profit. So now the problem is fill the knapsack. So output desired is a collection of items that can fit in the knapsack with maximum possible profit. Maximum possible profit. This is the problem. Now there is a very simple formulation for this problem. It is called integer linear programming formulation, and this will again study in detail when we study approximation algorithm. This formulation is very useful. So we formulate the problem, and not integer linear programming, linear programming. So a linear programming. In short, this is called LP formulation for this problem, fractional knapsack problem. So in this linear programming formulation, what we do is we take variables. So how much fraction of each item we are taking? So we take the fraction, choose a fraction xi. and here value of xi can range from 0 up to a maximum of 1 of item I, capital I, with index small I. So ith item we take the fraction xi, and xi can have fractional value in the range 0 to 1. So we choose our solution like this. So our solution is this sequence of fractions x1 up to xn. This we have to output. Now there are some constraints that has to be satisfied. Now if this is our solution, then you can easily compute total weight of the items is sum of all xi wi. Better write this as wi xi. I is equal to 1 to n. This is the total weight of the items, and profit we get is very similar. Sum of I is 1 to n pi xi. So ith item, if we take fraction xi, it contributes weight wi xi and contributes profit pi xi. So now our objective is that we have to maximize this. Maximize the profit collected subject to some constraints. Subject to some constraints. What are the constraints? The constraint is that this should fit within the knapsack. So the collected weight should be at most capital W. So we write this as sum of I is 1 to n wi xi is at most capital W. And other constraints are that the variables are fraction between 0 and 1. So we write this constraint also. Xi lies between 0 and 1 for all I from 1 to n. So this is linear programming formulation. Maximize summation of pi xi, I varies from 1 to n, subject to the constraints. Wi xi, its summation from I equal to 1 to n is at most capital W, and all variables xi from I equal to 1 to n, they lie between 0 and 1. So this is linear programming formulation for the 0-1 knapsack problem. In short, LP formulation. Now a very simple example we'll take and see how we can solve this problem efficiently. A very simple example. Having 5 items, number them I1, 2, 3, 4 and 5. Corresponding weights are given 1, 2, 3, 4, 5. Profits are given, just reverse order 5, 4, 3, 2, 1. And capital W, knapsack capacity is given 8. Now can you solve this problem, and what strategy you use? Give your solution. So the idea is very simple. Take the most valuable item. First take it. Once we have taken it, again repeat the same process with the remaining elements, remaining items. So if you see, just simply find profit per weight. So just make a table of this profit per weight, which is most valuable item, Pi divided by Wi. Just make a table. So first item is most valuable, having value 5 by 1. Second, this is 5, 4 by 2 is 2. Second item. Third item is 1, fourth item is 2 by 4 is half, and last item only 1/5. So just make a list of item sorted by in decreasing order of profit per weight. So first we choose the most valuable item. So initially our problem is I1 up to I5. So this is our initial problem. Just all this collection of items, weights, profits and knapsack capacity. This is our original problem. So first we take first item. It has weight is equal to 1, profit is 5. So take it. So it will fit in the knapsack, we can easily take it. Now so once we take first item, problem becomes smaller. So what we do is choose. So in the solution format, initially we have not taken anything. So in the solution format, x1 up to x5 we write, initially we have not chosen anything, all 0. This is our initial solution, partial solution. So next this leads to, we take the first item. Our partial solution is 1 and 4 zeros. This is our partial solution. What is the remaining smaller subproblem that we get? First item we have already taken. The remaining items. So we list the remaining items. Knapsack capacity will also decrease. So we write them 2 up to 5 we take. Smaller subproblem we get I2, 3, 4, 5, having weights and profit. Weights are 2, 3, 4, 5. Profits are 4, 3, 2, 1. Now knapsack capacity, weight 1 is already there. So the remaining, what is the remaining capacity? It is 7. Capital W is 7. And we already have this partial solution. So now we have this partial solution together with a smaller subproblem. So just observe that here we are getting this information even before solving the subproblem. So we are incrementally building the solution. Again repeat the same process once again. So now next in our list is the second item, is most profitable. So we choose the second item, it has weight 2, it can fit in the knapsack, we put it in the knapsack, our subproblem becomes even smaller, knapsack capacity is also decreased. So this leads to next partial solution we have. First two items we have taken 1, 1, 0, 0, 0 and the remaining subproblems are 3 to 4, 3, 4, 5 and weights are 3, 4, 5. Profits are 3, 2, 1. 3, 2, 1 and remaining knapsack capacity is 7 minus 2 is 5. So now this is the smaller subproblem and this is the partial solution. Again we repeat the same process. Next most profitable item is item 3 having weight 3. It can fit in the knapsack. Again we reduce our problem into smaller subproblem. So this leads to, now we have first 3 items. Our solution is 1, 1, 1, 0, 0 and 2 remaining items are 4 and 5. I4, I5 having weights 4 and 5, having profits 2 and 1. Now knapsack capacity 5 minus 3, remaining knapsack capacity is 2. So we write capital W Wi Pi, capital W is 5 minus 3 is 2. Now again we repeat the same process once again. So next most profitable item is 4. It has weight 4, but our available knapsack capacity is only 2. It cannot fit, so we have to take a fraction. We take a fraction half. So half of 4 is 2. It will fit in the knapsack. So we take only fraction half, and our problem is solved. So finally it becomes, we get our solution 1 1 1 half 0. The remaining sub problem you can write, but it is not necessary because problem is already solved. 5. Yes. Knapsack capacity 0 means our problem is solved. Yes. So we get this solution. So fourth item, it has weight 4. Our knapsack capacity is only 2. Weight 4 will not fit in the knapsack, but we are free to choose a fraction of the item. So we choose the maximum possible fraction that can fit in the knapsack. So we have to take half. 4 multiplied by half is 2. 2 fits exactly in the knapsack. This is the reason we take fraction half. We cannot exceed the knapsack capacity. So we get our solution. Profit we can compute. Profit computed is 1 multiplied by 5 plus 4, 3, half multiplied by 2. So we get 13. So this is the maximum possible profit that we can get. And here this is greedy algorithm. And what is our local choice? This is our local choice. Sort the items in profit per weight. Start from choosing the first item, which is most valuable. This is our local choice. And next we will prove that this local choice leads to global solution. This is the most difficult part. So complexity of the algorithm, you can easily see it is only n log n. Big O of n log n. This is complexity of sorting. Sorting based on profit per weight. So time complexity is very low. So greedy algorithms usually they have low time complexity. It has only n log n. Now the most difficult part is proving the greedy choice property. Greedy choice property. So the greedy choice property that we need to prove is that choosing items in this order, in profit per weight order, in decreasing order, will lead to globally optimal solution. This is the most difficult part, and we'll prove this. So first we write our algorithm, then we'll prove by induction that this algorithm works for all values of n. So now we write the algorithm and prove its optimality. So we write our greedy algorithm, call it greedy knapsack. Inputs we take set of weights, profits and knapsack capacity, small wi, I ranging from 1 to n, and profits pi, I is from 1 to n, and knapsack capacity capital W. So these are inputs. So step 1 is we sort the items in non-increasing order of profit per weight pi divided by wi values. So we perform the sorting, and just for simplicity we assume that Second step, our assumption is that P1, after sorting we get this 1, 2 up to finally Pn divided by Wn. So this is our assumption. It will simplify our proof. Third step, so base case is trivial. Suppose we have only one item, then what we do is check that if it can fit in the knapsack, if W1 is at most capital W, then return our solution 1. So 1 means take item 1 completely of fraction 1. This is step 5. Otherwise, else return this fraction capital W divided by W1. So else case means W1 is larger than the knapsack capacity. So we have to take maximum possible fraction. The maximum possible fraction that we can take is capital W divided by W1. So this is 7th step, return. Now the remaining possibility, otherwise if n is not 1, not the base case, W1, again this is simple case. Suppose first item is at least the knapsack capacity, then again simply return the maximum possible fraction that we can take, and our knapsack is full. So problem is solved here itself. So in this case, just return the corresponding fraction. No need to take any more items. This is capital W divided by W1 and all zeros. This is our solution. Otherwise, if the first item is not fitting completely in the knapsack, means we get a smaller subproblem. So next, reduce it to a smaller subproblem. 10th step, else case, we get smaller subproblem. Solve the smaller subproblem. Call the solution y2 up to yn. Recursively solve this greedy knapsack smaller problem. Greedy knapsack smaller problem is first item is missing and knapsack capacity is reduced. So set of weights are W2 up to Wn, set of profits are P2 up to Pn. Knapsack capacity is reduced from capital W to just subtract W1. So this is our smaller subproblem. Solve it. Suppose this is our solution, y2 up to yn. Now simply combine this solution. So we have to choose the first item in the else case completely. First item is taken completely. So we return finally our solution. Return our solution. First item 1, remaining we know the solution y2 up to yn. So this is a very simple recursive algorithm for recursive greedy algorithm. Here we are getting only a single subproblem. Now the difficult part is we have to prove that this algorithm gives optimal solution. Means if we have any other solution, then this is either same or better than the other solution. So we prove this by induction. Proof is by induction. So how we prove? This is our statement Pn, that this greedy knapsack with weights Wi, I is 1 to n, Pi, I is 1 to n, and capital W gives maximum possible maximum profit possible. So this is our induction statement Pn. We use mathematical induction. So first basis is simple. Basis is simple. So base case is n equal to 1. So n equal to 1 is trivial. Here we have covered here. If n is equal to 1 case we have taken. If the item fits completely in the knapsack, we choose it completely. Otherwise, the maximum possible fraction that we can take. So first case, it will give maximum possible profit, because if you replace it by any other item, it will have less profit. So first basis is trivial, basis holds. So basis n is equal to 1, we have Pn is true. So induction step, we assume Pn minus 1 to be true. Now we have to prove that, to prove Pn. So if you see the algorithm, our assumption says that here in step 11 we are solving the smaller subproblem, and our assumption is assumption is that this solution is optimal to the smaller subproblem. So this we use. Now how to prove this greedy property? Here our idea is simply compare our solution with any other solution, show that our solution is better. So we use exchange. How we use exchange? We'll see. So just consider any other solution. Consider any other solution. So call it y1 up to yn. Again, I have in the notes I have written the variables y. So just distinguish it with this y. This, they are different. Otherwise it will create confusion. So consider any other solution, call it y1 up to yn. Just compare it with our solution. So it should satisfy all the constraints, and the constraints are, so all constraints are satisfied. So we should have the weights I is 1 to n, wi, yi, this should be at most capital W, and our profit is this sum of all I is 1 to n, pi, yi. This is our profit, and we rewrite the profit in slightly different way to simplify our computations. Write this as sum of I is 1 to n, pi divided by wi, yi. So call this as profit of any other algorithm. Profit of other algorithm. So this is for the case when So in this case, when n is greater than 1, so n is greater than 1, suppose if we have the first item itself fills the knapsack, then we return this solution, and you can easily see that this is optimal solution, because if you use any other item, its profit will be reduced. So this case is also trivial. We are assuming that this is not the case, means there are at least more than one items are used in the solution. So we are considering this case. This case we are considering the general case. So general case, in our solution, first item has weight 1. So this will prove that in any optimal solution, in the last case, first item we should take it completely, otherwise will not get optimal solution. So this will prove. Take any other solution, call it y1 up to yn. If y1 is 1, then nothing to prove. It matches with our solution. Just combine with solution of the small sub problem, and we get our solution. So nothing to prove. Only thing we have to consider is the case when this y1 is less than 1. So any other solution such that y1 is less than 1, it is not matching with our solution. We have to show that we can get better profit by making this 1. So what we do is we use exchange. Exchange means take the first item, fill it such that fill it completely so that this y1 becomes 1, and replace it with any other item. This idea we apply and show that, compare the profit, show that our profit is increased. This is the very simple idea. If the other algorithm is not taking first item completely, replace first item with any other item so that first item is taken completely, show that the new solution has better profit. This is the idea we apply, and mathematically we prove this. So here we have written profit of the other algorithm. We have slightly changed the notation like this. It is sum of all profit per weight. Just observe that these are in decreasing order, means P1 by W1 is having maximum value, and Wi yi. So this way we write. So now again just rewrite this as this is equal to P1 by W1. So just assume that. So here we have seen our observation that P1 by W1 is greater than or equal to P2 by W2, and so on. This inequality holds. So next simplification what we do is just replace each Pi by Wi with P1 by W1. So P1 by W1 is having the maximum value. So we get inequality. This quantity is less than or equal to if we change this to only P1 by W1. So we get this inequality. Rewrite this as this is upper bounded by sum of, just change it to I is 1 to n, P1 by W1, rest is Wi. Just take this out, P1 by W1, sum of all, I is 1 to n, Wi is less than or equal to P1 by W1. So here just use earlier inequality, use this inequality, capital W. So here what we have proved is this is profit of our greedy knapsack. See, so this is formal proof of our this statement, this one. Now general case we consider. So general case, again as I have said, we have to perform exchange. So once again we consider this, consider line 12, n is greater than 1, Wn is less than capital W. So to prove optimal solution has y1 equal to 1. So here we use exchange argument. So once again same idea, consider any other solution y1 up to yn, consider y1 up to yn with y1 less than 1. So just use exchange idea. So here also we have two cases. Case 1 is y2 up to yn all are 0. So this case is easy to prove. Profit of other algorithm we get, you can easily compute as y1 p1 is less than p1, because y1 is less than p1 and this is at most p, profit of greedy knapsack. Why? Because in greedy knapsack first item is taken completely, so profit of our algorithm is at least p1, but profit of other algorithm is y1 p1, y1 is less than 1, so it is less than p1. So case 1 is proved, case 1 when all y2 up to yn are 0. Now the general case we consider, we use exchange argument. Case 2 is when some yj where j ranges from 2 to n is greater than 0. So here we exchange. So here what we do is exchange some fraction, call the fraction zj, and how much this should be, at least greater than 0 zj, at most yj of, so jth item we are taking fraction zj of it, so zj has to be at most yj. This much fraction of wj we take it out with w1 replacement, w1 such that, so we are doing replacement of some fraction of w1 with some fraction of jth item, we are swapping. So item 1 its weight is getting increased, item j its weight is getting reduced, such that net weight is same, and we show that our profit is getting increased. So this is the idea, and the equations are, so for first item it is y1 w1, this is extra weight plus, no, this is already weight, existing weight, extra weight is zj wj, and we take it such that with this constraint it has to be at most w1. So these are the inequalities. Now just compare the profits. So this is new weight of item 1, new weight, and also new weight of item j. It is getting reduced to wj minus zj wj. So weights are getting changed like this. This is new weight of item 1, this is new weight of item j. Condition satisfied should be this and also this. So we have performed the exchange. Now just compare the profit. So total weight, just observe, total weight is same. The amount decreased of j is added in I. So total weight remains the same, it will fill the knapsack. So for new set of solutions, weight constraint is already satisfied. Now just compare the profits. So write the two expressions. Profit before exchange is a very simple expression, sum of all I is 1 to n pi yi. Just break this in three parts. For item 1 it is P1Y1, item j it is PJYJ, and the remaining is I is not equal to j, and just remaining I am writing like this, not equal to j and 2, j and 1. Just next new expression, profit after exchange. So again 3 parts, profit of first item P1 Y1 plus, you can verify the expression ZJ WJ divided by W1 plus new profit of jth item, we have reduced the fraction ZJ plus the remaining is same, I equal to 2, I is not equal to j to n PIYI. So third term remains the same in both, before as well as after. Only difference is in the profits of first 2 items. So just subtract and see what is the difference. So if we perform the subtraction, profit of after minus profit of before. So you can perform the computation. I will just write the result. We get this as, after computations, ZJ WJ P1 minus W1 minus PJ by WJ. So now you can easily see this is at least 0 because the items are sorted according to profit per weight. So what we have proved is that given any other solution in which y1 is less than 1, we can always perform exchange so that y1 becomes 1 and our solution is better. So greedy solution is always better than any other solution. So this way we prove our greedy choice property and that our algorithm is optimal. Any questions?